What's algebra? What do we mean when we talk about algebra? What does it mean to you? It's not really a right or wrong answer to this, but... Yeah, often you might think of it as when we're using letters in place of numbers or letters involved in it. And something I'll tell you, this is probably one of the more challenging units. It's short. We'll be finished by next Friday, which is right before March break, right? So it's relatively short, but it is a tricky one. And what I will tell you is in every grade after this, more and more and more of the course relies on algebra. So this is something that we're going to do some more complicated algebra in this unit, but then the rest of the course won't have all of it. It'll still have algebra, but not some of the stuff that we're doing here. But like it's coming, right? So grade 10 has more, and grade 11 has a lot more, and grade 12 has a lot more. So this is not something that goes away. This is math. There's always people who complain and they're like, I liked math until they started using X in there and introduced it. Whereas it's like, that's math. I mean, that like math is not just adding and subtracting numbers. The concepts involved in mathematics starting in grade 9 almost exclusively use algebra. Okay, so keep that in mind that this is a big one. There's a couple of things in it. What we're doing today is not too bad. There's a lot of terminology. You don't need to know all of it after today, but you will need to eventually know most or all of the words we're going to talk about. Some of them I'm sure you've heard, some of them maybe you haven't. But you'll have some time to get to know them and use them. But like from now on, I will use them a lot when they're relevant. If you ever don't understand something, you're more than welcome to ask. You can remember that you will have a list of definitions, and we're going to do examples to try to illustrate all of these definitions. So you'll have all of this. But just so you know, like I can imagine if there's a word you didn't understand, it would be hard to follow the lessons. It would be hard to follow what somebody's talking about, whether it's me or somebody else. So you do need to know these words. And the other thing that I will say, and so down the road a little bit in a few days, so today's going to be easy, but then we're going to do something that all of a sudden is going to mix up and muddle a whole bunch of us, and it's going to become more difficult. So when we get there, I will point it out, and it's one of those moments where you have to really focus and be like, how am I going to make sure that I keep these things separate? It's similar to the idea of when you're adding, you use a common denominator. When you're multiplying, you don't, right? But here's something else that you can really think of. So throughout the unit, I will talk a lot about why these things are true. And I think a lot of students, especially in the earlier grades, don't think about why. They just memorize the rule and they move on. But if you understand why, you're way less likely to make a mistake. So it's really useful, it'll be valuable to you to spend some time thinking about why this is true, why this equals this, why this equals that, why when we're doing this, this is how we do it, and when we're doing something else, we do it differently. Okay, so I'll talk about that, and that's not a small thing. Sometimes we don't need to know why to get the right answer. We just need to know the rule with what I call conceptual understanding. But that understanding is key to building on your knowledge and making your life easier in the long run. Okay, so keep that in mind as we're going through this. Ask questions if you have them as we go. Make sure you copy down all the different examples and be thinking about why the examples fit or why they don't or that sort of thing. Okay. All right, let's get started. So the first definition is a term. So typically speaking, a term refers to a group of numbers and or variables. Okay, it can be mixed together. Terms are going to be separated by adding and subtracting. So for example, this is how we're going to do this. We're going to put examples below each of these definitions. For example, 2x on its own, I'm just listing them right now, is a term. Okay, 10 is a term. Negative 8b. These are all things that are being multiplied together. 10 is a special kind of term. It's just a number, but it still would be a term. 2x is 2 times x. all together it makes up a term. Negative 8 times b all together makes up a term. You could have a single variable be a term as well. Doesn't have to be things multiplied together, but it can be. Now what about some expressions with two terms? X plus 2. Two terms. One of them is x, one of them is 2. 3x, how about minus 2y? One of the terms is 3x. The other term is negative 2y, or minus, you think of minus, so you're subtracting 2y. Maybe a plus b, going to do one more. R squared plus r. Again, we're not going to see a ton of things like r squared in this course. We will do some, but every year you get a little bit more and more complicated elements in algebra. So r squared plus r is an expression with two terms. One of them is r squared, one of them is r. They're being added together. A variable term is just quite simply a term with a variable in it. So for example, a. (5g) negative y x squared. Sometimes in mathematics we use other symbols, not really in grade 9, but starting in grade 10. Here's one of them. Has anybody ever seen that symbol before? You'll see it a lot in grade 10. It's the Greek letter called theta. A lot of mathematics has its roots in like Greek history or Latin history, so a lot of the terms come from Greek language or Latin, that kind of thing. And then the other thing we're going to do sometimes is we're going to list things that are not whatever definition we're talking about. So in this case, not 5, because that's just a number. Not negative 1, not 0, not a billion. Those are all just numbers. They don't count as variable terms. Everybody okay so far? We can compare that to a constant. So we do use the word, we do say variable term sometimes. Like we do often, all the time, we'll be like noticing that a term has a variable in it. But we don't use that language a ton, the variable term. But we'll use it a little bit today as we're getting used to it, that kind of thing. But something we do use a lot is constant. So constant term or just constant, okay? And a constant is a term with no variable. So all those numbers at the top there, oh, I'm going to add another one. What about this? This is a really good one. Pi. I'm adding that to the not category above as well. Pi looks like a variable because it's a symbol. It's another Greek letter, but it's a number. It is not a variable. And you can even have something like 2 pi. That's just a number. 2 times pi. 2 times 3.14. It's about 6.28. But it's just a number. Okay? Special number, but just a number. So, a term with no variable. 5. Negative 1, 0, all of those definitely that we did above. Pi, a billion, or let's do a million this time so we don't have to write out so many zeros. Okay? All of those things are constants because they have no variable part. Okay? So obviously What are not constants? X, Y, anything that has a variable in it. 10y, yeah, it's got a number in it, but that doesn't make it a constant. That's a variable term because it also has a variable. Here's another big term that your teacher will use over and over and over again for the next 4 years. And it's something that I think this is one of the trickier ones. Like, how many people have seen this word before? Yeah, so some of you have, some of you haven't. And that's fine. That's totally fine. And it's like, new words aren't hard. It's just a matter of getting familiar with them, right? It's just a matter of using them enough that you remember, oh yeah, that means that. So coefficient is the number in front of a variable, the number that's being multiplied through by the variable. Okay, so for example, 6x. So what is the coefficient? That's how you say that word, by the way. I don't think I said it yet. Coefficient. You don't have to be able to spell it yet. Someday probably a good idea to be able to do that, but if you can't spell it, that's one thing. What's the coefficient? So this is how we talk about things in algebra. What's the coefficient of the term 6x? And this is how we can start to sort of like communicate and share these ideas. It's 6. Very good. The coefficient of the term 6x is 6. What about negative 3y squared? The coefficient, this one's a bit trickier. Somebody wants to answer, be careful. No? Oh, I see why you say that. Good, that's a good point. We don't need to worry too much about this right now, but the 2 is only on the y. If it was like this, then it would be on both. It's not, so it's just on the y. Somebody else want to try? Nice, and you included the negative. It's negative 3. When we're talking about coefficients, we include the sign. So the first one was positive. When it's positive, we don't usually list it. We don't usually mention it. You might say positive 6 just to be clear. You might write it because you really want to because you've made that mistake in the past or something. We don't usually, but when it's a negative, obviously you have to. Okay? Any questions about any of that so far? This is just terminology. We'll use it throughout the course. Okay, next one is like terms. Like terms are terms that have exactly the same variable part or variable component. And the special note here is that only like terms, we're going to do this today and tomorrow, only like terms can be added or subtracted. If terms are not like each other, you can't add them together. In fact, if I go up here, I see some examples of that. They're not like each other, so that's why they're written separately. These ones are not like each other, so they're written separately. Does that make sense? So like terms have the exact same variable part, and it's special because you can add them. Okay? Which we're going to do today. So here's some examples of things that are like terms. And I'm going to do like lists across. 3x, negative 4x, and x are all like terms. Like all 3 of those examples are like terms. They're like terms because they all have x. Right? They'll have the exact same variable part. How about 8a squared, 0.5a squared, and 7.3a squared? They all have a squared. That's important. I'm going to talk about that more in a moment. They all have a squared. That makes them like each other. What about AB, 3AB, negative 10AB, They all have A and B. A times B is the variable part. It's exactly the same in all of those. It's kind of interesting that looking at examples, like good examples, things that are true, only helps us a little bit. To me, it's when we look at examples that are don't fit the definition. When you start to go, oh, okay, now I understand the difference. So something like this, not 4m and 4mn. They got the same number. They both have m. Why are they not like terms? Because one of them has n and the other doesn't. So they're not like terms. Here's another good one. Negative 5z 12z squared. Why not? Because one of them z and one of them z squared, which is z times z. So they're different. That's another really important one. That's one you see all the time. And probably not today, but like next week when we sort of complicate things a little bit more, some of you will try to add those together when it's a z and a z squared, or an x and an x squared. Obviously, something like A and B are not, because they're different letters. Another example. This one won't come up a lot, but we'll look at it anyway. 2xy squared and 3x squared y. Why are they different? Because the squared's on a different variable. You might say it looks basically the same to me. They both have x, they both have y, they both have squared. But I'm here to tell you, turns out, no, they're different. So what does that mean? It means you can't add them. If you have one question with both those terms in it, they may not be added together. What does that mean? Well, who knows? Like, that just means that you're going to do something, or like totally depends on the question, what you're doing with the question. That's coming way later, but that's the point of like terms, is when you can or cannot add. Now, I think this definition is coming maybe on the next page a little bit, yeah, or on the back of your page. We also refer to expressions as a mixture of terms. Adding, subtracting, multiplying, dividing, something like that is an expression. So each one of these questions has an expression in it. All we're going to do to start is state the number of terms. So for question A, the expression is 3x. That's a word that I'll use all the time, by the way. Expression. So it's got a 3 and it's got an x, which is two things, but how many terms? It's just one term, because when things are multiplied together, we call it one term. Compare that to B. How many terms does B have?
2.
2 terms, very good. That's pretty easy, right? Like, a lot of what we're going to do today is easy. Gets a bit harder, but it's not too bad. How many terms does the expression in C have? The back, say him. 3, very good. What about this one? Jacob?
2.
Yeah, good. That one's a weird one. I don't think you'll ever see a question that's got that many variables in it like that. So it's just here to be kind of a example of, yeah, it's got a whole bunch of letters, but it's still just 2 terms, because all of those are multiplied together and all of those are multiplied together. So 2 terms, but that's not really something we do, at least in high school mathematics. I'm going to add an extra one here. What about, this is a trick question. Again, trick questions are useful to think about and explore, sort of like where it's going next, or make us think a little bit. They're not things that we would put typically on a test. 2a plus 3a. How many terms does that have? Why is it a trick? So there's no right or wrong answers if I put a tricky question up, because it's just for us to think about. What do you think?
It's something to do with that they're like terms.
Very good. So it looks like there's 2, but this question to me isn't finished. It's not what we call fully simplified. So I can add them together, and we're going to talk about this in a minute. It works out to 5a. And if you simplify it, if you do the work and you finish the question, it only has 1 term. If it's written like that, it looks like it has 2. So what's the correct answer? And like, I wouldn't get hung up on that. That's my point. That's why it's a trick question. It really depends on what you're talking about, or who's asking the question, or why it matters. Okay? Any questions about that? Feeling okay so far? So when a question says collect like terms, what it's actually asking us to do is add or subtract. Something else I want to say, this is kind of like when I made a big deal about BEDMAS a while ago. These questions are asking us to collect like terms. If a question doesn't say that, it doesn't mean you just jam everything together and add whatever you want. Like, you can only ever add or subtract like terms whether the question instructions are saying that or not. And generally speaking, if you can add like terms, you always finish a question by adding like terms. It's kind of like lowest terms in a fraction. You always do it. So for now, I think your instructions will say collect like terms. It might say simplify or something like that. It might say add or subtract like terms. It all means the same thing, but generally speaking, we always will collect like terms, and you only ever can collect like terms whether the instructions say that or not. So don't think, oh, this is a different kind of question, I'll just start mashing stuff together. The whole point of what we're talking about today is to learn you can only add or subtract like terms. And again, going back to that definition, what are like terms? Terms that have exactly the same variable part. So what's your gut feeling? We kind of already did one, so you probably know the answer to this one. What's your gut feeling that's the answer to this? 7x. Very good. That's correct. How many people were thinking it's probably 7x? Right. Nice. Why is it 7x? When you are, go ahead. And literally speaking, this is exactly the same thing as it, like, if I have 3 apples over here and I have 4 apples over here, I got 7 apples. That is literally what this is saying. This is 3 x's. I'm talking about x, and I've got 3 of them. If x was 5, because that's probably what's going to happen. X is representing a number. If x was 5, I have 3 5s, I have 15. That's what 3 5s is. Like, think about that. This is where the conceptual understanding comes in. So I literally have 3 of them over here. I have 4 of them over here. How many do I have altogether? I've got 7. Okay? So think about that when you're adding like terms. I sometimes add cats and dogs, or apples and oranges, or bananas, or something like that. Like, we do think about it that way. Okay, what about B?
I think it stays the same because they're not like terms.
Good job. That's a trick question. You can't add. Again, this is not necessarily the kind of thing we're going to do a lot of. Somebody might have thought, well, I'm going to try and I'm going to go 6AB. We'll talk more about this later, but this is wrong because you're supposed to be adding A's and B's, and now you're multiplying A's and B's, and you can never change adding like that into multiplication. Like, that just doesn't happen. So this is totally wrong. Okay? So it's not 6 of anything. If I have 4 cats, and I also have 2 dogs, what do I have? Well, 6 pets, but that doesn't work that way in mathematics, right? So you've got 4 cats and 2 dogs. That's what you have. Okay, you can't add them together. Not in mathematics. What about C? This is one single question. This is one expression. How many terms does it have? You're thinking about when we start putting things together. How many terms does it look like it has? 4. There's 4 things. Okay? But I notice 2 of them have X and 2 of them have Y. I'm going to do this question in 2 steps. So I think it highlights a few things really nicely. So I want you to write this down as well. We're always going to do equals on the next line, right? So I'll start with the 7x just because that's what came there first. I talked about this before, but notice I curve my x's. It's a nice habit to get into. Probably most of you will, if you're not already, you will start to do that eventually. Almost everybody does. There's 2 ways of doing it. I do it that way. The other way is like that. So you do like a little, I don't know what that is, a Z or something, and then you cross it. Okay? And it highlights the difference between variable x and the multiplication symbol. I said this before, we'll very rarely use the x as a multiplication symbol, but it does show up once in a while. Remember what we said? What is the coefficient of this term here?
-2.
It's -2. So the whole coefficient has to go with it. That's a common mistake. People forget to bring the minus over with it. I'm subtracting 2 x's over here. I better still be subtracting 2 x's over there, right? So I'm regrouping. We call this kind of regrouping and putting like terms side by side. Now I have -3y plus y. So this is important because I haven't changed the question at all. I've just moved things around. And it's nice because now I can see that I've got the 2 x terms, which I've underlined in green, side by side. Those are the ones I can add together. And the 2 y terms that are like each other, that I've underlined in orange, those are the ones that can actually be added together. And look at this, we still have integer skills that have to happen. So this is 7 minus 2. That's easy, it's just 5. The variable part never changes when you're adding. So you just look at the coefficients, 7 minus 2. That part you can do on your calculator. You try to put an x into your calculator, it's not going to like you. Okay, so if you want to use your calculator when you're doing algebra, you still have to know the rules. I do 7 minus 2 on my calculator. And this is -3 plus, thank you very much, 1. When it's just a y, the coefficient is 1. So -3 plus 1, which is -2. Y. I'm going to make a note of that. And 5 minus 2 is 3. And now we're done. No! I hope you didn't write that down. Anybody copy that down? This is what people do, though. They're like, okay, I'm supposed to collect like terms. I'm going to regroup them together because I know I put the x's together. Then I'm going to put the y's together. Then I'm just going to add them. Now I'm done. Now I'm going to mash it all together. And then you got this great answer here that's correct. And then you make a mistake because you just keep trying to smash stuff together. You got to know when to stop, and it does start to get a bit more complicated. You got to know when to stop. So I'm gonna mark this like this. I'm gonna leave it there. Common mistake. How do you know when to stop? I mean, practice. Just getting used to it and getting familiar with it to the point where it's feeling natural and you kind of get it. You know what I mean? That's the only real way that you can do that. All right. I kind of got in the way of this question. So this question has a whole bunch of terms. Some of them can be added together. The point of this question is this one has x squared. This one only has x. We talked about this already. They're not like each other, so they don't go together. So what I'm going to do, starting from left to right, is I just look at what the first one's like, and I flip through, and you might highlight or underline with different colored pens or pencils, at least when you're starting. Some of you might not want to, you might think that's overkill, but it is a strategy. So I'm going through and I'm looking for other x squareds. I found one. Any more? Nope. I'm going to change colors. My next term is just x. I'm going to go through and see if I can find any more. Yep, there's one. My next one, there's a 5. We call that a constant. And there's another constant. Those are like terms. They can be added together. That's what we've been doing. 5 minus 1, we know how to do that. That's no different than the integer math we've been doing. Okay? They always have been like terms. 5 minus 1 is something you would have done in grade 2. 5 minus 1 in grade 9 is still the same thing. Okay? So I'm going to regroup them together. 6x squared minus x squared. And so people say, but I thought you were adding. I thought it was 6x squared plus something. Now you've changed it to minus. And this is what I'm saying. That's not how you look at it. You always look at the coefficient, the thing in front of the term. It always goes with it. Plus 2x plus 3x plus 5 minus 1. There's my greens. There's my reds. There's my oranges. So 6 minus, that's 1. It's going to be 5. 2 plus 3, also 5. 5 minus 1, 4. And that question's done. That's where you stop. 5 plus 5 plus 4 is 14 somethings. I don't know what. Any questions? Sometimes it worries me if there's no questions. People should have questions. This is tricky stuff. Some more definitions. I already talked about expression. Now I'm using that word again. So an expression means like a question. Sometimes you can talk about different expressions within a question, but sometimes expression is just sort of a global term for the question or whatever. So monomial is an expression with one term. Let's do some examples of these as well. Three x squared. Why would monomial mean that? What's mono? Where have you heard that prefix before? Anywhere? No?
Does it mean 1?
It does mean 1. And the one place that I can think of you may have heard it is you get stereo audio, which is separate channels coming out of two different speakers, a left and a right. And mono is when it's like all the same coming out of every side or every speaker. If you ever looked in computer settings or something like that, or like a music player, it might have those in the settings, and that's what it means. Mono is something that's used in other places, and it still means 1. But anyway, binomial, an expression with two terms. So this would be like x plus 2 is a binomial. Why? Good. Why does that word mean two things? Where have you seen the prefix bi before? Bicycle is one that I can think of, right? 2 wheels. That's a thing with 2 wheels. There's lots of other places that you might see that. Trinomial, an expression with 3 terms. So one we just saw is like x squared plus 3x plus 2 or something like that. So where have you seen that before? Tricycle, yep. Where else? Triceratops, I like it. Triangle, that's a good mathematical one, that's right. So there's lots of places that we see tri. And then polynomial means an expression with many terms because poly means 3. You've heard of polygons. That's a shape with many sides. No specific number, just some. Could be only a few, could be lots, right? We mean that as a more general way, that's a polynomial. So a polynomial could be a binomial or a trinomial. All right. Degree. The degree, this is a very specific one that will only really come up mostly in this unit, so it's something you kind of want to memorize. It should be fairly simple, I think. The degree of a term is the sum of the exponents. If it only has one exponent, it's the exponent of the term. So some examples. The degree of x squared is 2. The degree of a, why is the degree of x squared 2? Because the exponent is 2. So what's the degree of a? 1, because it has an exponent of 1. It's hidden, but it's there. The degree, I hope this isn't a question. Oh yeah, I'm gonna leave that one. Never mind, we're gonna see that in a minute. The degree of a polynomial is equal to the degree of the term with the greatest degree. So again, for example, the degree of 3x squared plus 5x plus 1 is equal to the degree of the term with the greatest degree. So what's the degree of the first term? 2. The second term? 1. The third term? We'll talk about that again in a minute. But it's 2, because that's the biggest degree. A squared minus 2a cubed plus 7a. What's the degree of that one?
3.
Good, 3. Because the middle term has a 3. That's the biggest exponent on a variable. So it's 3. Okay, state the degree of each term. Again, this is pretty easy once you get the hang of it. So what is it? 2. Next one. So the next one is different, and I heard a couple people give different answers. I heard 1, I heard 0. Did anybody think anything else? What do you think? Did you have your hand up? No? Which one is it?
1.
Why do you think that?
Because 14 times stuff.
Okay, good. So the 14 has an exponent of 1. But we're only looking for exponents of variables. So it would be 0. Because this is like, I don't know, 14x to the 0. X to the, but there is no x, but it could be anything. X to the 0, a to the 0, b to the 0. It's got all of them, I guess. Because they're all just 1. So when you see a constant, again, this is something to make a note of to yourself. Constants have a degree of 0. What about this one? The degree, I'm not going to say equals 1 because this doesn't equal 1. The degree is 1. It's got, we already talked about that. It's got an exponent of 1. And we're not doing F or G. Scratch those ones out. Get rid of those. We're going to do E. So I got a 1, I got a 2, and I got a 4, so it's 4. Pretty straightforward. Turns out the degree of something is really important, but you're not really even going to get to learn why until grade 12. D was 1. The last part of our lesson today is as a standard. Standards are useful in mathematics so that we're all speaking the same language. And one of the reasons why it'll be important to you is when you're doing these questions and you write your answer and you go to check the answers, it'll look the same. Because if you write things out of order, it will look different. Imagine you wrote a 14 as a 41. And you're like, oh, but that's what I meant. I got a 4 and a 1 there. Same thing. Like, no, we have a standard. We have a tens column and a ones column and that kind of thing. But like, you can't mess with that. You're going to say, yeah, I like to write numbers backwards. Like, what? Nobody's going to have any clue what you're talking about. Okay, so this is like everything in life, really. It's about communication. So there's 2 things that we're going to talk about here. As a standard, it's not so much about right and wrong unless you're asked specifically to do it. Throughout high school, students always ask, do we have to write it this way? Do we have to? In some cases you do. In a lot of cases you're just going to. You're going to want to. But we always write polynomials alphabetically. So starting with the first letter of the alphabet and going forward, or forward for you. And we always write exponents in descending order. What does descending mean? Going down. So the biggest exponents first as a standard. So if I was going to rewrite this one, what would I start with? 3x squared. Very good. Then I'm going to choose the 4x, and that's a positive 4x. So I have to put a plus sign in front of it. And then we always finish with constants at the end. You may not have one of each. That's got a 2, a 1, and a 0. You don't always have all of them. That's how we would do that one. I just want to go over this again. Maybe it seems obvious, but this is important. These mean the same thing. This isn't wrong. It's just a little weird. It's just kind of out of order. So we start with the biggest exponent, and then we go down from there. Exponent of 2, exponent of 1, exponent of 0. And that's just a standard. So if I go back up to this question, it was written strange. If it's written in the right order, you can just look at the first term and say it's degree 2. Okay, so what about this one? The other thing we do is we write them alphabetically. So I'm going to start with the A term, then the B, then the C. Again, that's a positive 2C, so plus 2C, then the D. This one doesn't have a constant. So after that one, I'm done. Again, standards are just good so we're speaking the same language. So if we're each doing an algebraic question, at the end, our answers would look identical because we wrote them in the same order. If one of us forgot to, we'd be like, oh, ours look different. You might look carefully and be like, oh, that's why they're different, because one of us has it written backwards or something. Okay, that's all.